So, hi everyone. So today we're going to build ML monitoring from scratch. This is a real live coding session, and actually I'm going to discuss a little bit about the technologies that we are going to use. But everything here is based on open source tools, and we'll actually write it from scratch. We'll assume that there is a model that runs in production, and then show how to monitor that model. Cool. So feel free to ask any question in the workshop, and let's begin. So before diving deeper into the monitoring architecture, we need to discuss some of the tools that we are going to use. So how many here are familiar with Kubernetes? Awesome. Okay. So Kubernetes is basically, it's like an operating system. So if you have a traditional operating system that you run applications on top of one machine, Kubernetes is just like an operating system that runs on multiple machines, right? So I can install applications on Kubernetes, and then these applications run, in a distributed way on multiple machines. So it's not really an operating system, but I just like explaining it that way. And it's very common for machine learning platforms to be based off Kubernetes. So for example, what can run on this? So here there could be, a container that runs an inference for a machine learning model, and so forth. And we're actually going to build our monitoring solution on top of Kubernetes. We're going to use AWS, but the concepts that you see in this workshop are not specific to AWS. You can apply the same things for Google Cloud or Azure. And specifically, we're going to use three main services in AWS. So the first one is S3. S3 is this bucket storage. You can basically store a lot of data very cheaply on S3. ECR is a container registry. You can basically upload Docker containers to ECR and then serve them in Kubernetes. Let me know if something is not clear. And then EKS is just like a managed Kubernetes. So AWS manage that for you. So usually when setting up infrastructure on top of AWS, it looks something like this. Okay, so lots of input boxes and complex configurations, and just changing one thing here could cost thousands of dollars. So we are not going to build our infrastructure this way. But we're going to use a tool called Pulumi. So Pulumi is a tool very similar to Terraform. It lets you define your infrastructure as code. Okay, so in this example, I have this Python line that creates a Kubernetes cluster, and this Python line that creates an S3 bucket, and then I run Pulumi app, and this thing will basically spin up those resources for me. And there are a lot of advantages for that. So I can send this code, this infrastructure for code review, and I can basically share it with my colleagues. So that's another tool that we're going to use. And let's get right into it. So the first thing that I'm going to do is to draw the architecture together of what we're going to build. So we will assume that we have a machine learning model that runs in production. And let's just, draw it right here. So this is an ML model. And by the way, this is a really cool tool called Excalidraw, just for, drawing some stuff. So we have this ML model that runs in production. It runs in a Kubernetes cluster. And I'm going to show you the code for that in a second. So this is my Kubernetes cluster. And now what we're going to do, we are going to build two main parts. So first of all, this model, so the way it works is that it gets requests, right? For example, predict me something based on specific features. So let's say this is the input to the model. And then, inside that service, it calls model.predict, creates a prediction, and then returns that as a response. Okay, so the user gets back the prediction. Does that make sense so far? Cool. So the model receives inputs and then sends back the prediction. And that runs on top of Kubernetes. So the most basic concept in monitoring, before you can even start to monitor your machine learning models in production, you need to actually store this data. You need to store those inputs and outputs. And we are going to use S3 for that. So S3, just as a reminder, is this bucket storage where you can store data very cheaply. So the first component that we're going to build is something that lets you store our inputs and outputs of this model in S3. So how is this thing going to work? So we are going to use Kafka. And Kafka is basically a way to it's like a queue. Okay, so you can publish, each prediction to Kafka, and then someone else can consume those from the queue and do whatever it wants with that. So Kafka is really useful for when you have real-time data. You have a stream of real-time data that you want to do something with this data. Kafka is useful for that. So we are actually going to add some code to our model here to send this data, the inputs and outputs, to Kafka. So this is going to be Kafka. OK, so we have an ML model running in production. This is going to be based on Fast API. It's basically this Python library for, it's a web framework library. So you can create HTTP servers. Each prediction is going to be sent to Kafka. And then, OK, so now we have Kafka with all the predictions streaming into it. The next stage would be basically to have this component that consumes predictions from Kafka and stores them in S3. Okay, so this is a component that we'll have to build ourselves. And it is called, let's call that the inference store. Okay, so this is going, we'll call this the inference store. Let's zoom out a little bit. Oops. OK. So we have the machine learning model running in production, sends predictions to this Kafka queue. And then we have this component that consumes predictions from this Kafka queue and saves those to S3. So let's do that. So it's basically going to store those predictions to S3. And sorry for my drawing. I'm not the best drawer in the world, even though this app is amazing. Cool. So now we have a centralized place where we have all of the predictions in production stored. The next phase would be to actually monitor this data, right? So the next phase, we will actually build a different component that reads from this S3 bucket. Okay, so it's going to be a scheduled job that runs every once in a while. In this case, we are going to run it every 5 seconds. So essentially, it will connect to the S3 bucket and then calculates things like the different statistical properties of the features. And if you'll have, for example, data drift, this is something that we would want to calculate in this component. So one of the things that it can do is, for example, compare the training set to the production set, okay, and give you some score on how much the model drifts from the training set. So essentially, this component is going to take the data from the S3 and then aggregate that to machine learning specific metrics. So we are going to call this the inference aggregator. Okay. And now we basically have metrics that we calculated. So we have different statistical properties, we have drift scores, we have all sorts of things like that. And we are going to send this data to an open source tool called Prometheus and Grafana. So how many of you are familiar with Prometheus and Grafana? Cool. So Prometheus and Grafana are tools to help monitor usually not machine learning, but rather software system. For example, it can monitor the CPU of different systems, the RAM, etc. And we are going to actually send those metrics to Prometheus and Grafana and visualize our models right there. So this is our architecture. Let me zoom out a little bit. And just to recap, we have a model. It's running in production. It has inputs and then produces the prediction. So every inputs and prediction we're going to send to a Kafka queue. So we have a queue with all of our predictions. That will basically will have a component called inference store that basically consumes predictions from this Kafka queue and stores them in an S3 bucket. And then we're going to have this aggregator, which calculates different statistical properties, compares production to training sets, etc., from the S3 bucket and send those to Prometheus and Grafana. Does anyone have any question on the architecture? Yeah. Yeah, OK, so the question was if there is any reason to use Kafka instead of just doing something like this, right? Instead of just model straight to S3. So the reason that it's considered a bad practice to write directly to S3 is because S3 is, the writes are very slow. OK, so the storage itself is very cheap, but it takes time to write from, it's not real time. It can add a lot of latency to your model. So we don't want to add any latency or want to add as least as possible. So that's why we will we will use Kafka, which is exactly for this use case. Yeah, so the question was if this S3 bucket is really necessary, why not just use Kafka or write it to a different topic or anything like that? So when monitoring your models, basically you don't just monitor each prediction, because it's possible, but it's mostly useless. So one of the things that you want to do when monitoring models is to take a lot of data from the last day, the last week, or things like that, and then compare that to your training set. So if we only used Kafka, so Kafka is good for for just every prediction, do something, check something. But then if we want to take a look on the bigger picture, we need that data stored somewhere. And also this data is useful not only for machine learning monitor, but also for training purposes and all sorts of things like that. OK, so let's get to coding. So the first thing that I am going to do, I'm going to show you, So the last question, because thank you. Yeah, so the question was, what if we had not real-time models, but rather batch models, would we need all of this? Would we need this Kafka? So the answer is not. It's no. You can just write directly to S3. And actually, right now, I'm going to show how the training of an example model, how do you write that to an S3 bucket. So this is our architecture. And now we are actually going to implement all of this thing. So this is a real live coding session. There might be bugs. So help me find them. Thank you. OK. So we are going to start from an existing model, just a random, very simple model that we are going to use. It's just a dummy model. It's Iris. So Iris is just receives as input some details about the width and length of different parts of the flower, and then predicts what is this flower. So just a very simple model. So this is some code to train this model. This is a great tool, by the way, called DeepNote. Instead of Jupyter Notebook, it's really useful. I recommend to check it out. So we trained this model. And by the way, can you see the code? OK. And we have this model trained. OK? So the next thing that we want to do, zoom? Yeah. OK, so just sample example training code for models. Is this good? Can you see that code now? Thank you. OK, so the first thing that we want to do is basically store our training data in that S3 bucket. The reason why we want to do that is because one of the most important use cases for ML monitoring is to detect drift between training and production. So we need that training data stored somewhere. So when we want to monitor that, we can compare training to production. So storing the training set is very easy. This is a pre-existing code here. So basically, we take the, so we have this training set, right? We have this data frame, which we use to train the model. It's using LightGBM in this case. And then this is just a very simple code to store that training set in S3 bucket. So before continuing, I want to introduce one more concept. It's called Spark. So Spark is a system, it's very similar to Pandas in a way, or to NumPy, but it lets you basically distribute calculation across multiple machines. So this is a really useful piece of software. And when you have lots of data, that could be useful. So we're actually storing our training set right here in this S3 bucket. Okay, so this is a very simple example of how to store data in S3. And if you had batch models, you can just do that. You can just take your data frame and then write it to S3. But that's not the interesting part. So now, we trained that model. And now this is a boilerplate for a model that runs in production. Okay, so this is where we start from. It's basically a very simple Fast API server. Fast API is similar to Flask. It's a way to build very simple HTTP servers in Python. So we build this endpoint /predict, and it receives the inputs of the model in the request, calls model.predict, and then returns the prediction as a response. Make sense? You can do it like that. Thank you. Okay. So we can actually run this. So let's run that. So I'm going to run and then explain what I'm doing right now. So the way it works is that this model runs on Kubernetes. Okay? And we touch on what's Kubernetes in the start of the session. But the idea is that we have this code, and then we wrap this code in a Docker container. Okay, so this is an example for a container that just runs the HTTP server. And then we deploy this model to Kubernetes using an Helm chart. So Helm is just like you have the App Store on your phone, right, where you can install applications. So Helm is just like this App Store for Kubernetes. It just lets you deploy applications on Kubernetes. And we just built our own Helm chart that deploys this model on Kubernetes. So let's talk a little bit about the directory structure here. So we have the model. This is the code. This is the Docker file. And then we have the Helm chart, which is used to deploy the model to Kubernetes. So this is how it looks like. A bit scary, but not too much. So you have the path of the image and so forth. And yeah, so that's the structure. And then we use a tool called Scaffold just to deploy this Helm chart to Kubernetes cluster. Any question? Okay. So let's get back here. And we have the first error in the workshop, so we have no build access. Let's fix that. So I essentially needed to log into my AWS, to the ECR, and now it should work. So this thing essentially deploys the model, the Docker container, on Kubernetes. So this is just the model itself, and now we are going to build the monitoring part of that. So let's wait a couple of seconds here. So this now builds the Docker image, and then pushes it to the cloud, and then deploys that to Kubernetes. And this code is going to be open source, so you can reproduce that by yourself later on. Cool. So while it's running, let me tell you a little bit about how I initialized all of this infrastructure before the actual code. So as mentioned earlier, we used a tool called Pulumi. So Pulumi is a tool for defining your infrastructure as code. And this is something that I cover in depth in my previous workshop on how to build a machine learning platform from scratch. So we actually build this Pulumi code from scratch, and it's available on YouTube if you want to look at it. So essentially, the way it works is that we create a Kubernetes cluster on AWS. We create an S3 bucket, and then install all of our software. So this is not something that I would like to focus on right now, but it is something that you can take a look on in depth in the Building an ML Platform workshop. So let's see what's going on here. Okay, so it's still deploying. And let's start actually coding the monitoring part. So let's get back to our architecture. And the way it's going to work is, so the first thing that we need to do is just every time that there is a /predict, every time that we make a new prediction, we want to send that prediction to Kafka. Okay, so let's code that. So we're going to use a Python library called IO Kafka. Okay, so it's called IO Kafka. And essentially, this library allows me to push data to a Kafka queue. Okay, so the way it works, I need to initialize that. So let's do that. So first of all, when the Fast API server initially starts, we can have this event called startup. And then we want to just, initialize the Kafka here. So the way it works is that I can create a new object of IO Kafka producer and then push data to that. So IO Kafka producer, and then we need to provide it with the URL of our Kafka. Okay, so we're going to do that in 1 second. So this is an object that we will want to use from our model.predict. So let's store that. Okay, so this is this ugly global variable that stores the object that can produce Kafka topics. So we'll need to do something like this. And then each time that we have a prediction, we can just log that to the Kafka. So the way it works, it's very simple. So we are going just to do something like this, ioproducer.send. And again, just as a recap of what we're doing, we have this model running in production, and we want to push each one of these predictions to Kafka. So let's do that. So we want to send a JSON here. And in Kafka, there is a concept called topics. So it's like channels, different queues. So for example, for each one of my model, I could have a different Kafka queue. So in this case, let's call that my model. And then we can just send a JSON. And by the way, feel free to ask any questions, or if something is not clear, on the go. So, okay, so what do we want to send to Kafka? So we want to send our features. So we have actually 4 features here: sepal.length, sepal.width, and so forth. And we want to send the prediction itself. So let's do that. So let's take the first feature, and then just pass it from the request. So we have 4 features. So this is just, let's just send all of those features to. So there is a really nice trick in VS Code. You can just click Command D and then write, and then switch the same word simultaneously. So these are our features. And this is the width. Okay, and let's put a comment here. So those are our features. Now, the next thing, we want to send the actual prediction. Yeah, so the question was, what if I have hundreds of features, for example, right? Yeah, so, well, this toy monitoring platform is not going to be able to do that. But check us out later on in the booth, because that would be, no, just kidding. Yeah, so it's essentially, I don't think that would scale to hundreds of features, but yeah. So the way to scale it probably is not to send JSONs, but some kind of binary format. Otherwise, just one scale. Okay, so features. And then we can also send our predictions. So in this case, it's a very simple multi-class model. It just predicts what is the variety of flower. And then we have also the probability for that. So first of all, we have the prediction. And this is ypred. So ypred is just a result of model.predict. So ypred. And then we also want to send the confidence, so you can monitor the confidence of the model. Yeah. Yeah, so the question was, so that we are actually awaiting on the send to Kafka. And that could add latency, you're right. So first of all, just back to your question, Kafka has way lower latency than just writing to S3. So that is OK. But probably in production, you would want to do it in an async way and not like this, which is a bit more complex. There are many ways to do it. One example is a sidecar. Another example is to create a background thread that just sits and sends that predictions. But yeah, this won't scale to billions, but it will be sufficient for less than that. So let's finish logging our predictions here. So the confidence is just this. And this will essentially log our predictions to a Kafka queue. Now, one thing that we need to do here, so this function has a string arguments. We just need to convert the JSON to that. OK, so that is the first step. So if we get back to our bigger picture, we have the model running in production. It's based on fast API. And then we log the inputs and outputs to a Kafka queue. Now, let's see if, OK, so it seems like our app is up and running. And let's try to actually send an HTTP request to that. So this is the IP. We can just click send, and it doesn't work. So I told you there will be bugs. Yeah, so probably I'm in the wrong directory or something. OK, so while this is running, we can start writing the second component of this workshop, which is called the inference store. So the inference store, essentially, we send our predictions to this Kafka queue. Now we need someone to read it, right? And push them to an S3 bucket. So we are going to write this application using Spark. So the way it's going to work, let's create another service here. So let's create a directory. We'll call it inference store. Let's put it in services. And then we're going to have two files. So the first file, we're just going to call it sync.py. This is going to run in the background, always read that data from the Kafka, and store that in an S3 bucket. So this is what this script is going to do. So the first thing that we need to do here is, it's to initialize the S3 bucket and all that. So I have it in my deep note. So this is, and let me explain what this code does exactly. OK. So let's remove everything that's not necessary here. OK, so this essentially creates this Spark session. And now we can write Spark application using that session. So I think we don't need those two. And we also don't need all of that. OK. And this is the S3 bucket that we actually want to store predictions in. So the first thing that we need to do, so let's think what are our steps here. So step one, we need to create this Kafka source, right? So we need to create a source where we can read the predictions from the Kafka. Step two, we need to do some kind of processing. This is going to be very specific to this model, unfortunately. But then step three, we want to write that to S3. So these are our steps. And before actually write them down, let's see if my scaffold is working. Yeah, it wasn't in the correct directory. Scaffold up. OK, hopefully this will work. So there is so the way to to interact with Kubernetes, it's a command line tool called kubectl, kube control. So for example, I can get all of the containers that are running in this cluster. So the command is kubectl get pods, and for some reason it does not respond. That's strange. Yeah, so here we have our Pulumi code that actually, initialize this cluster. So we have the kube config for that, the authentication for that Kubernetes cluster right here. So let's just store that. Pulumi. And this will essentially, take the Kubernetes cluster details and then just write them to some directory so we can check why it's not interacting with our cluster. But then, but let's continue to writing the code right here. So first, we need to read predictions from the Kafka source. So the way to do that using Spark, so we have a function called read stream, and we want to read from Kafka, right? So this is the first step. Second step, we need to provide it what is the correct Kafka URL. So we can do that just by giving, so there are a couple of options here. We can provide what is the correct Kafka URL here. And then here we'll need to put the actual Kafka URL. So we'll figure out what is that URL when the Kubernetes cluster will actually work. For some reason, it just doesn't go up. Let's try that again. So we create this Kafka source. We read from this Kafka URL. And as a reminder, we sent all of our predictions to a specific Kafka topic called my topic, or my model, right? So topics are different channels or different models that I have here. So let's configure that to be my model. So essentially, I am reading from this topic, and then other options that I want to put here. So let's say that this script is not running, and we want to make sure that it reads all of my historical data. So we can tell it to basically start from the earliest data point that it can see. And then we don't want this thing to fail. So if there was some kind of data loss or something like that, we just want to disable that. So in production, you probably want to handle exceptions with this thing. And yeah, and this is basically how we created these input streams that constantly reads from Kafka topic. Any questions so far? Okay, let's see what's going on with the Kubernetes here. Okay, let's see if it works now. Awesome. Okay, so just repeating what I've done. So I run kubectl get pods, which is the way to interact with Kubernetes clusters. And then I can see all of my containers that are running in this cluster right now. Cool. Okay, so what are we doing? Okay, so I think what we can try right now is to check if actually, our model actually works. Just try to send it some HTTP requests, make sure that we get a response. So before doing that, let's get back to our model. So in my model, we had this main.py. And as a reminder, when I initialized the Kafka topic, we didn't enter the correct URL here. So let's do that. A kubectl get SVC service, so it's something that can be accessed from outside. And then let's take the correct Kafka URL. Okay, and the port is this thing right here. So let's put it. And now we can actually try to run this container on Kubernetes clusters, send an HTTP request, and see if we have something in Kafka. So let's run again scaffold dev. And again, Scaffold is a tool that I use. It's really convenient. If you're working with Kubernetes and Dockers, I highly recommend trying it out. It basically builds the Docker image, push that Docker image to anywhere, and then deploys in Helm chart, for example. So it really makes all of that part streamlined. So right now, it seems to be built. OK, so it built the Docker image. And now it's starting to deploy the Helm chart. And after the Helm chart will be deployed, we'll basically port forward. We basically do some kind of tunnel to make sure that we can access our model. So this thing is currently running. Cool. So let's continue writing the code in the meanwhile. So this was the first step of having the Kafka source. And if I'm going back to the architecture here, so we are currently building this inference store component, and basically we get inputs from the Kafka. So now, the next, let's go actually to step 3, which is writing this data to S3 bucket. So the way that we're going to do that, so here we use spark.readStream. And what we're going to do in this step is instead of readStream, we're going to use WriteStream, right, to write to the S3 bucket. So WriteStream. And here we are doing something interesting. So we are actually using a data lake here called Delta Lake. Now this part is a bit more advanced, but don't worry about it. It's very similar to writing to an S3 bucket. But essentially, data lakes are a very convenient way of managing data in S3 buckets and things like that. So we call this WriteStream function, and we want to write it to the S3 bucket in the Delta format. And now each time that we have a new prediction, we want to append it to the end of the table. So the way to do that would be to use output mode append. Awesome. So one interesting thing that could happen here is that maybe some of our features change in production, right? So maybe we redeployed a new model version, and suddenly we have new kind of features. So we want to make sure that the schema of the S3 bucket is merged. And the way to do that is to configure this option. It's called merge schema. And let's set that to true. Know that in production, we probably want to have some more management for this part, right? We don't want just to merge schemas as is. It should be more managed. And then let's run start. And we basically need to provide it with a path. Where do we want to actually store this data? So we initialize the Kafka source, and now we are writing the stream to a Delta Lake, to S3 bucket. But we do need to provide the path. Where do we want to actually store all of that? So let's do that. So we have this S3 base URL, and let's store that in my model, which is the name of this model, and then /serving. And finally, we do want to run this basically infinitely. So each time there is a new prediction in the Kafka queue, just store that in the S3 bucket. Some other things that another thing that I need to do here, another option, is basically to have this checkpoint location. You can just, I'd rather not explain exactly what it is right now. It's just something that you have to do. But let's just store the checkpoints in this location. And yeah, so we have this script, the inference store script. Right now, it reads data from Kafka and then writes them to an S3 bucket. Cool. So let's see what's going on with our Kubernetes here. So we can see that it actually deployed our Helm chart, but there is some kind of maybe error because it says that one of the replicas are pending termination. So let's see what's going on. Let's just see all of our pods. And then this is our pod. So you can see that it's currently crashing. So we can get logs on that pod to understand what is the exception. And the issue here is that import so for some reason, I think import it's just auto-completion from VS Code. Let's remove that and save. And this is really cool. So I can save, and then scaffold will just, in this case not, but in general, it will just rebuild the Docker image and then push that to the Kubernetes cluster. So this will take some time. OK, so let's keep coding here. Awesome. So we actually created this Kafka source. And the first step is to write to the S3 bucket. But we do need to do some processing first. Why do we need to do some processing? Because in Kafka, we sent JSONs. But in S3, we want to store that as per cat, or a different format. And to do that, you do need to provide the schema of the data. So let's create the schema for our data. So this is how it looks like, struct type. And I need to import that somehow, so I think it's right here. So this is going to be our struct. Okay. Laura? Okay, so I'm just opening a Zoom link so we can share it with the people at home. So let's see. Sure. So this is the bit.ly link. 1 second. And I'm going to write it in a bigger screen. OK, so this is the bit.ly link for the Zoom, but for some reason it doesn't connect. So we'll just give it some time. OK, so let's rerun here the scaffold dev, and in the meanwhile we can keep. OK, so I think this is not working, but I'm just going to zoom in a little bit more. OK? That's accidental. Is it better now? OK. OK, so we are building the inference store, the component that actually streams predictions from Kafka to the S3 bucket. And we did the first step and also the third step, the last step, which is actually to write it to S3. But now we need to do some processing for all of that to work. So let's define our schema here. And basically, for each one of our features, so remember we had this CPAL-LAN feature, we need to provide what is the type of that feature. So in this case, it is a float. And let's make sure that this is imported. And we just need to do it for all of our features. So let's duplicate that 4 times. And then we had all of our features right here. So I'm just going to copy that. Awesome. So we did that for the features. And finally, we need to do it also for the predictions. So prediction is actually, it's the number that represents a flower. So it's just going to be an integer. And then the confidence, which is just the probability of this prediction, is going to be a float. So this is our schema. And now we basically need to convert from Kafka JSON to a Spark data frame. So it will know what is the correct format here. So to do that, we have these PySpark functions. And let's just do something like this. So we have from JSON. So this essentially converts a string, a column in the PySpark data frame that is a string, to a JSON. Okay, so we can provide it with the name of the column, which is just value by default. So this is how Kafka sends that. Okay? This is how this stream works. It just sends the entire JSON as the value. And we probably need to convert it to a string. So this is the first step, the first argument, which is our JSON. And then the second argument is our schema. Okay, so parse this JSON according to this schema. And then we can basically store this column as a new column. Let's call that just JSON. Okay, so essentially we parsed the JSON, we parsed the string, and now we have a column in our data frame that represents the JSON. And now we want to, to explode this JSON. We want all of our fields to be just columns of the same data frame. So the way to do it is something like this. We want to select all of the fields that inside our JSON. Okay, any questions so far? Okay. So basically, this is the inference store script. As you can see, so it was a bit, it was a bit hassle to do this processing, but it is pretty simple. You have step one, we are creating this Kafka source, and then we do some processing using the schema, and then the first step is just to write all of that data to S3. Let's save that and see what's going on with our Helm chart. Okay, so we run our model in the Kubernetes, but we see some kind of error. Ini takes one position arguments, but two were given. So I think the reason for that is we need to, maybe it's like this. Okay, so just it's not the same argument. Yeah, I think that should work. Let's save. And now it's pretty cool. It just builds the Docker image and redeploys that to Kubernetes. So this is what's cool about Scaffold. Okay, so in the meanwhile, let's recap what we did so far. So we basically have this machine learning model that runs in production using a fast API server. It's this part. We send each prediction to a Kafka topic. And then we built this component, 3 steps. 1, take all the data from Kafka. 2, process it. 3, stream that to an S3 bucket. And this is the idea of this component. Okay, so let's try to run this. Okay, awesome. So now it seems like the model is actually running, and we did some port forward here. Then let's try to send a request. So let's zoom this in. So this is the URL, localhost /predict, and these are our features. Send, loading a bit too much for some reason. Let's see if everything is okay with our cluster. Okay, so the model is actually running. We can actually do kubectl logs. And it seems to be running. That's a bit strange. Okay, let's try to port forward that again. So port forward, the name of the service is just my model. And then this is the local port, and this is the remote port. Okay, so let's try to do that. Okay, we have a connection. Okay, it's interesting. Maybe the problem here, so we see that there is communication between this port to Kubernetes. Maybe the problem here is that the Kafka, it's for some reason can connect to that Kafka, right? Let's see if I made a mistake here. So Kafka CP, let me take a look on my notes as well. So this is the Kafka producer, bootstrap servers. Oh, okay. So we need to run ioproducer.start. So that's the reason it won't work, and then it just blocked the prediction. Let's save that again. And now Scaffold, this is magic, because before that we just needed to build a Docker image manually. So now it rebuilds the Docker image, pushes that to the Kubernetes cluster, deploys the Helm chart. Okay, interesting. So now we have port forward, and let's try to use the original port. Yeah, for some reason, it's still not working. Let's see if I missed something. So we have startup event, on event startup. So this is called on the initialization. Server return no data. But let's see if we have any logs. So we can take a look on the logs of the production. Server seems to to work fine. Let's try to port forward it ourselves. Okay, so we just port forward it ourselves, send an HTTP request. These are our features, and this is the prediction. And we didn't see it right now, but this data was actually sent to Kafka. So now let's try to run our second component of actually storing this data on S3, and then see if the data is actually being stored there. So the way to do that, we can just, let's deploy the inference store. So I need to create a Docker file for that. And let me copy that. So this also will be in the GitHub. I think I have it here. Yeah, so this is the Docker file for the inference store. It's pretty standard Spark Docker file. It looks a bit scary, but just something that you copy and paste. OK, so now we have this image. We need to make sure to add that to the Helm chart, right? So let's Google Spark application CRD, which is how we deploy Spark applications, and just copy the code right here. Let's find a Python example. So they have lots of examples right in their example directory. Yeah, OK. So this is an example for how to deploy Spark application on Kubernetes, and we are going to do it on a Helm chart. So let's create a new template here. We call that inference store.yaml. And then we don't need all of that. Let's call that. So this is the name. Let's call that inference store. We want Python, version 3. Mod cluster, it's the type of communication with Spark. And now we need to provide the image. So the image, we'll just copy that from here. Just Scaffold will actually override this image in order to build it locally. So let's use values.inference store. And then we need to provide it with the, with the correct path of the Spark application. So in our case, we just call that sync.py. I think that should work. Yeah, OK. So Spark version, we don't need. Let's just put the correct version here. And we don't need all that and all that. Let's keep it as lean as possible. But one important thing that we need to do is to configure the service account, the user in Kubernetes that actually runs this Spark application. The reason that's important is because we want to make sure that this pod will be able to access the S3 bucket. Okay, so this is also something that we cover in depth in the previous workshop in the building ML platform from scratch. So let's see what is the name of our service account here. So Kubernetes is just like a REST API. You can run kubectl get or just send an HTTP request. Service account. And let's find what is the name of this service account. It's this S3 service account, which can access S3 buckets. So let's use that here and here. And let me just compare that to the original example to make sure I am not missing anything. OK, yeah, I missed that part. Cool. And this part. OK. So now we configured our Helm chart to actually deploy Spark application, specifically the inference store, to the Kubernetes cluster. One thing that we did not do is to add that to Scaffold, so it will know to watch for those files and make sure to build and push and all that stuff. So let's do that. I can just duplicate my model here. Let's call that inference store. And then we can override the name of the image, so it will push from locally. And I hope you can see the code and everything. OK, so this theoretically should work. Oh, no, it shouldn't, because I need also to provide the image from the Helm chart values file. So let's add that to here. We actually have it. OK. Awesome. So just to recap where we are right now. We are building this architecture. We have this fast API. It already sends all of the predictions to Kafka. We are now deploying this inference store component that consumes all of those predictions and pushes them to S3. We just finished writing that code, and now we are actually deploying that using the Helm chart to the Kubernetes cluster. Cool. So if everything was OK, you should just run scaffold dev, and it should work. Let's Control-C and up and enter. OK, so the next step is to first we'll verify that we actually have all of our predictions here in this S3 bucket. And then we will build this inference aggregator, which will send ML-specific metrics to Prometheus and Grafana, where we will be able to visualize our metrics. So let's run the scaffold up. OK, so all of that, all of the work we have done so far was just to save the predictions of the model in an S3 bucket, of real-time models in S3 bucket. So that's, storing predictions is really, really important. It's important for auditing purposes, it's important for retraining, it's important for monitoring data drift, performance degradation, and all that. And it's really cumbersome. So when the model gets more complex, it's getting, a bit worse to do what I just did right now. It worked mostly because it was a very simple model. So actually, we built an open source component. It's called InferenceDB. And the idea is to stream inferences of real-time ML models to a data lake, just like what we did now. So actually, it's not released yet. We're actually going to release it right now. So the idea here is that all of the work that we have done so far with, going to setting the Spark application, the Kafka, all of that can be streamlined by InferenceDB and let you store all of the data from your models in production. And this is actually a production-grade system. So yeah, let's release that. And I would really appreciate your stars. So settings, and let's convert this repo to public. OK. And if you are using in production Knative, Kserve, any of those inferences, Seldon Core, this is something that you probably want to use. So the repo is Aporia AI/InferenceDB. And it works Helm install of this thing, and then you can create a special Kubernetes resource called Inference Logger, and that makes sure to log off your predictions from this topic to this S3 bucket. And there are tutorials for Flask and Fast API here and Kserve. Cool. So let's continue. OK, so we have something running here. Let's see if it actually deployed our inference store that we've just built ourselves. Yeah, OK, so it looks like the inference store is running. And let's use a tool called K9s. This is alternative to kubectl. It's a bit more convenient. So we can actually see all of our resources here. Let's take a look on all of our pods. And this is the inference store driver, which is what actually creates our inference store. OK. So it seems like our inference store just ran the Flask application. Probably I did some mistake with configuring the images. So let's go from scratch. So we have the scaffold. It basically compiles services inference store with this URL. And now we have the values. And this looks OK. And then in the YAML of the inference store, this also looks OK. What did I miss? So we have that inference store. OK, so this is the artifact override. Values. That's super strange. Inference store. Yeah, it actually should work. OK, so for some reason, it just creates the wrong image. OK, so let's just continue, and maybe it will solve itself somehow. Probably not, but maybe we'll have an idea after that. Oh, OK. So maybe that's the reason. So we have the incorrect tag here. Let's use the real tag. Save, and now scaffold should detect my change automatically and redeploy that, and hopefully that will fix it. Okay, so the final step would be to write this inference aggregator service, which calculates ML-specific metrics from our S3 bucket. And then we'll just create our dashboard in Prometheus and Grafana. So let's duplicate our inference store. Call that inference aggregator. And here we basically don't want to have all of that stuff, just the things for Kafka, so just normal Spark. But we do need to have here the Prometheus client. And this is basically the Python client for sending metrics to Prometheus. So installing Prometheus client right here. And then let's delete all of our code here. Most of it is going to be similar, like the initialization is similar, but everything else is going to be very different. OK, 1 second, sorry. Let's see if here it's now running. OK, so we redeploy the scaffold. Let's see if the image is correct now. OK, so we have all those pods. And for some reason, it did not deploy our inference store. Let's just run kubectl pods. Yeah, for some reason, I cannot see. Let's see if we have this Spark application running. OK, so it says pending rerun. And let's describe that to understand why it's not working. So describe Spark app inference store. OK, something happening here. Maybe it should just take some time, and we're a bit impatient. OK, so let's just continue. Awesome. So let's write this inference aggregator service. Let me make sure that I can see that. OK. Cool. So what we're going to do, we're actually going to read the data from the S3 bucket, aggregate it, and then send metrics to Prometheus and Grafana. So step 1, read data from S3. Step 2, we want to calculate aggregations, and we'll discuss which aggregations we're calculating really soon. And then the first step would be to send results to Prometheus and Grafana. OK, so the first step is just to read the data from S3, so it's pretty simple. This will be the data from production, so we can just do something like that. Spark.read, we save that in our Delta Lake, and then we need to load a specific path. So where did we have that path? In the inference store, because that's where we wrote this data. So let's go to the inference store and copy the path. OK. So this is the serving set. And for monitoring, again, training is also very important. So let's load the training set as well. So df training, and then it's very similar path, df training. OK, so that was the first step. We basically have a data frames for our production and our training set. Next, we want to calculate aggregation. And this is very interesting, because there are lots of aggregations that you can calculate. I mean, what do you even want to monitor? Right? There are many different options. And the problem is that it is also very specific to the model that you actually want to monitor. Right? Because different models have different data sets, different kind of metrics that you want to monitor. Everything is pretty much different use cases, NLP versus tabular, demand forecasting versus fraud detection. So this is really, really different. Here we'll just focus on our simple model, the Iris model. So let's say that we are interested in monitoring the average of some of our features. So actually for all of our features. So we can actually read all of our columns. So this is a list of all of our columns in production, right? And for each column, we want to calculate the average, for example. So let's just do that. So average on this column. OK, so this should be an array. And then we want to send all of those aggregations together to make sure that, not to miss any, to make it as high performance as possible. So we can do dfserving.aggregate. And essentially, we're now sending like this command to Spark, calculate the average of all of my features, and get the results back to me. Yeah. So now the way it returns that in this array. So we just need to do something like this. This is just something standard that you just copy paste all the time, the first .sticked, because I'm not sure why they don't just return the results, but yeah. And this is actually the results of our the first aggregation. So this is let's create this object, a dictionary, where we store all of our aggregations. Okay, so let's just append. It's like this. Let's see. Oh, so it's dict, so we need to do update. Wow, this line is really long, especially with the zoom. Let's try to do something like that. OK, so we calculate the average value for each one of our columns in production, and then store them in this Python dict. And let's do it a couple of more times. This is really ugly. I'm just copy and pasting that, but it can be in a better way, just combining all of the aggregations and sending them together. So sorry, this is average. Okay. So we want mean, and we want max. So let's assume that's what we want to monitor for this model specifically. And let's also add, the average of each feature on our training set. So let's do it in a normal way. So we want to do it. Per training and per serving. Okay, for now I'm just gonna copy paste that, but it's really, really ugly. And another thing that I need to do is just to give all of those results some name, right? So let's assume that this will be, let's put some comment here. So serving, average plus min plus max, and this will be training, average plus min plus max. OK, and then let's just give each result a name. So the result would be the name of the column, underscore the name of the aggregation, for example, average, underscore serving. And let's do it also right here, and also right here. So these are pretty simple aggregations, just for some feature statistics that are important to monitor. But more complex aggregations could be, for example, measuring the statistical distance between each feature in the production versus the training set. This is one example. Another example could be shop values, right? If I want to get explanations for each one of my predictions. Another example could be to actually, if you have delayed feedback, if you have ground truth after you make the prediction, for example, 3 months later on, you can calculate AUC, ROC, and F1 score and things like that, or even your own custom metric. So I can actually code those things specifically for my model in this script. OK, and let's do the same thing for training. So this is training. Oops. Training, so and this is average, and I'm just going to do it really quickly because probably it's very boring. This is min, and this is max. This is also min, this is also max. There's got to be a better way to do this loop. But we don't have a lot of time. And this should be also serving. Training. Okay, so let's recap on what we are doing. So we are building this architecture. We have the model that sends predictions to Kafka. From Kafka, there is this component that consumes those data points and stores them in S3 bucket. And now we are building the inference aggregator component, which reads data from S3, aggregates it, and then sends it to Prometheus, which is exactly what we're going to do right now. So let's do the Prometheus part. Yeah, and the way it's going to work, so we install this Prometheus client library, and we can just, import, I think it's called registry. Yeah. So this is the registry where we're going to register all of our metrics, and also we have a function called push to gateway, which is the function we'll use to actually push the metrics to Prometheus. So this is pretty simple. We just initialize the registry where we have all of our metrics, and now we will just, so remember we added all of those metrics to this dictionary. I'm just going to iterate over this dict and just add each one to the registry. So metric name and metric value for this dict is aggregations.items. Yep. By the way, any questions so far? This is getting pretty heavy, but feel free to ask any questions. So let's push each metric to the registry. So in Prometheus, there are different kind of metrics. So for example, you can have histograms, you can have different types. We are going to use a type called Gauge. I think that's how you pronounce it. And then we can provide the name of the metric. Let's import that. So this is just a numeric value, right? Because our average and things like that are just numeric values. So, okay, Gauge, and then we need to supply some documentation for this metric. Because we don't have a lot of time, I'll just repeat the name of the metric. And then, let's see if this documentation is correct. Name, documentation. And then we need to provide the registry. Okay. So this is the metric. So this is actually the Prometheus metric. And now we need to set its value, which is just Prometheus metrics.set metric value. So we build this registry of metrics, and now we need to push them to Prometheus. Now, this is not such a good practice. Usually with Prometheus, you want to have this HTTP server that has /metrics endpoint, and then Prometheus will constantly pull metrics from that. But this is something a bit simpler. It's maybe easier and more convenient for batch jobs. So let's just push to gateway, and then we need to provide the IP of our Prometheus, or the URL. We'll find that in a second. Let's see what are the arguments here. Okay, we need to provide some job name, just any random string, like, I don't know, inference aggregator. And finally, we need to provide the registry. Okay. Awesome. So just to recap, we are building now this component, the inference aggregator. It pulls data from S3, both the serving and the training set, calculates different aggregations, and we can discuss more complex aggregations a bit later on, and then send all of those aggregations to Prometheus and Grafana. Let's try to run some things because we're writing a lot of code. Let's see if it now works. Yeah, for some reason, let me just try to delete that and retry, and if it won't work, I'll just show you the Grafana dashboard right away. Okay. Nice. So let's run scaffold dev once again. And basically, this is all the code that we needed to write. Okay, so we've actually built this custom component of inference store. We built this custom component of inference aggregator, and we push that to Prometheus and Grafana. So first, we read data from S3, right? And then we prepared a list of aggregations. So these aggregations are average, mean, max, etc. on each one of our columns, right? So basically, this code adds all of these metrics to a Python dict. So by the end of the day, the way it looks like, let's just put that as a comment. Just, age, if the name of the feature is age, then max serving, for example, then the value. And then age mean serving, and then its corresponding value, right? So it's just a dict with key metric name and value, which is the metric value. And then we do this for loop. So essentially, this is just a trick to iterate key and values simultaneously, right? So I'm doing dict.items. And then we have the name of and the value of that metric. And that's what we're pushing to Prometheus. Yeah, so gauge is like, so in Prometheus, you have different kind of metrics. Let me show you that. Never mind. So there are different kind of metrics that you can send. For example, you can send numbers. You can send histograms. You can send info, for example, version. So gauge is just a fancy name for kind of a number. But that's the easiest way to do that. Any other questions on this aggregation code? OK. Let's put the correct Prometheus URL here. Cool. And I see that it's finally running this Spark application. So hopefully that will actually work. But let's put the gateway, which is the component that we send metrics to. So Prometheus URL. And then the port is 1991. OK, should work. So before continuing, I actually need to put this final Docker container inside our Helm chart. So I'm just going to copy paste. So this is not inference store. This is inference aggregator and inference aggregator. And just copy pasting. Aggregator. So this will tell Scaffold to rebuild this image and push it to Kubernetes. And we also need to duplicate this Spark application. Now here there is an important detail. The inference store, let's get back to here. The inference store is a component that runs infinitely. And every time there is a new data in the Kafka, it just automatically pushes that to S3. Inference aggregator runs just for a batch, right? Just runs, calculates things, pushes that to Prometheus. So I need to make sure that this thing runs in a cron job. And the way to do that, so the Spark operator on Kubernetes has this different CRDs. It's called scheduled Spark application. So here we use Spark application, but I need to use scheduled Spark application. So let's take an example. So it's very similar. Just need to add, this. So scheduled Spark application, and then we need to add that. And then this is the actual template for the Spark application. OK, so this will run every 5 minutes, but we don't have that much time to wait. So let's change that to 5 seconds. And finally, we just need to put the correct image for the aggregator. So let's try to run all of this thing. And let's save that. And right now, it's probably running and compiling the Docker images and all of that stuff. So we'll give it some time. In the meanwhile, let's go to Prometheus and create a dashboard. So I think I already have some data there. So let me show you how you can create dashboards in Prometheus for stuff like that. So let's in Grafana, sorry. So let's port for this thing. So this is Grafana. And the port is just 80. So let's do that like this. So this is my local port. And let's just go to Grafana. OK, so this is the Grafana that I installed in the Kubernetes cluster. I did that beforehand. And now we can create a dashboard. So let's go to Dashboards. And let's create a new dashboard. So new dashboard. And now I can start adding widgets. Now, this thing is not so appropriate for ML. It can show like averages and numbers pretty well. But comparing distributions, for example, which is very important for monitoring, is a bit hard to do here. But let's add just, for example, the total predictions. Actually, I didn't add this metric, so let's do that. Let's add here the total predictions. So I'm just adding another metric, which is just dfserving.count, right? So now let's call this panel total predictions, and then use the total predictions metric. So let's, I have it from beforehand. And this is a time series. We're just interested in the value, so we can change the value here to stat. And this is the total predictions. Let's store that. And we have the first widget. So another thing that we can do is to display the average of a specific feature, for example. So we can do, CPAL, so this thing, simple weighted average serving. And let's say we also just want to display the value. So this was the value. But also we probably want to compare that to training, right? So let's add another metric called training. Cool. Okay, so this is just a very simple example, but you can see that the average in production is 16, and then in training it's 3, which might be a bit strange. Let's give it a name. So simple with average. Prod versus training. So this is essentially how you can build monitors, how you can build dashboards in Grafana. But it's not very well adapted to machine learning. It's really good for CPU and RAM and software metrics. And that's where Aporia and similar software comes into place. So this is still running. Let's give it a couple of more seconds. In the meanwhile, I want to show you Aporia. So we discussed the inference DB component, which is an open source component to help you store the data in production, just what we've implemented here, but production grade and a bit more advanced. So we just released it today, so go ahead and start that. And after having all of your predictions stored somewhere, which is really important, you can do retraining, you can do all sorts of things, but you can also monitor your models, right? And this is essentially how Aporia looks like. It's a dashboard that's really well adapted to machine learning. Okay, so it can also stream metrics, just the metrics that we built. It can stream that to Prometheus and Grafana. But it has support for a lot of different statistical distances and all of that stuff. And users can actually write their own custom metrics inside the tool. Okay, so if I want, for example, to write a custom metric, I just go to custom metric and just add this really simple Python API. That thing compiles to PySpark and then can be calculated on billions of predictions. So the first step of a monitoring system is visibility. You want to get visibility to what's going on in production. For example, all of the performance metrics from production, different precision, average, and things like that, and different data segments. For example, we can see that we have a lot of predictions between 20 to 26, of ages 20 to 26. Another component, important component in monitoring, we touched that just a tiny bit, is explainability. So I can actually go to data point screen and then see, okay, we have this male here, he's 50 years old, he has a driving license, and the model predicted that he wasn't going to buy insurance. And probably you want to understand why, right? So you can click explain, and this will basically generate the explanation for this model in production. So this is what we've implemented is a bit more simplistic because it aggregates data and you don't have this online slice and dice that you need, which is another very important component. And by the way, one of the cool things that you can do here is actually to change some of the values. For example, what if this guy was previously insured? And then click re-explain, and this way debug your ML model in production. So we touch visibility, explainability. Another very important part is monitoring and alerting, right? So I can actually, in a very user-intuitive user interface, create monitors, for example, for data drift, prediction drift, performance degradation, and so forth, and really customize what I am monitoring for each one of my models. And the cool thing is that you can actually take these PySpark scripts that you wrote, for example, this script, and just put it right into Aporia. So this thing will manage, so in this example, it's pandas, but this thing will just manage all of those metrics for you. So you don't have to maintain all of that infrastructure that we just try to build. Let's see if it's, okay, so I have an error. But I think that is essential, that is essentially what I wanted to show you, how you can actually build a very simplistic monitoring solution from scratch. And yeah, are there any final questions? So the question was if you are able to see here, things like comparing histograms, which I was not able to do in Grafana. Yeah, so there is like this custom dashboard feature, which is just like Grafana. I can actually, I have just two widgets here, but I can actually build my own dashboards. But the widgets are more specific to ML models. For example, distribution comparison, as you can see here, or time series, like that. It's a great question. So let me comment on the comment, just one thing to add right there. So the comment was, okay, you can just stream the data straight to Prometheus and then use Prometheus to calculate averages, right? So that is true, but you can't calculate more complex things like statistical distances, AUC, These are things that are really hard to calculate in Prometheus because PromQL, the language behind Prometheus, is not that flexible. It's just so that's why I chose to demonstrate this kind of architecture, because here, relatively easily, you can add metrics that's already supported by Spark. For example, AUC is already supported by Spark. So this is something that you wouldn't be able to do, and fix me if I'm wrong, without something like that. You do need some kind of batch processing. And yeah, so the question was if I'm using Pulumi to configure Kubernetes services. Yeah, so it depends. Initially, we did do that a lot. So you can see that I initialized the Kubernetes cluster. But then later on, we install Helm chart using Pulumi. So this installs Kafka, and this installs Prometheus, and so forth. But to be honest, for your own Helm chart, it doesn't work so well, just from experience. So for your own Helm charts, I would use something like Scaffold, which can actually be used in production, or just straight Helm install on the cluster. Or Git, there is Flux, which is like, yeah. Any last question? Cool, so we are actually doing a raffle for this driving car. I forgot that name. So you can go to our booth and maybe you'll win that car. Thank you so much. If you have any questions, I'm available on email, alon@aporia.com, LinkedIn. Thank you.